Jacquillat, Professor of City and Transportation Planning at MIT. This is the MIT Mobility Forum organized by the MIT Mobility Initiative. Today, it's really my great pleasure to have Professor Alex Jacquillat actually join us again to present his work on the flexibility and coordination in the on-demand transportation. Right. 2 years ago, he actually came here to talk about the urban area mobility. Today is another area of major interest from Alex. Before I formally introduce Alex, I do want to mention a few, particular one norm of this forum. Right. Compare most of the Zoom-based seminar. This, I would say, is the most active audience. Right. And we persistently encourage everybody to contribute. Right. So the expectation is that everyone contribute one idea, either in the format of a comment or questions. Please type into the chat, right? Given today's topic, I prepared a short poll to get a flavor of people's interest in this, right? So today's topic, later Professor Jacquillat will describe is the notion in the ride-sharing context. Instead of the door-to-door service, we'll consider the corner-to-corner service, right? You walk a little bit to be picked up, etc. So I'm launching a poll to get a sense of people's preference here. The settings are the following. Either Uber or Lyft are going to pick you up. So with a $3 discount, how long are you willing to walk to a pickup location? Okay. 70 people submit the answer, 90, 100, 120. 140. I'll give 5 more seconds. Okay, so all of the 184 audience, 155 submitted the answer. Let me share the result with you. Alex, can you see it?
Yes, I can see it. This is great motivation. The answer from my talk is 100 meters on average. So it's very much in the mode of this distribution. So I think that we're done.
That's interesting. Great. Yeah, thanks. So I'll stop the sharing there. So let me introduce Professor Alex Jacquillat. He's an assistant professor of operation research and statistics at MIT Sloan School of Management. He holds the chair of the 1942 career development. His research focuses on the data-driven decision-making, including stochastic optimization, large-scale integer optimization, and machine learning. His primary interest lies in the problem of scheduling, operation, and pricing in the transportation sector, with a particular interest in the air traffic management and on-demand mobility and collaborative logistics. Alex has received numerous of research awards, include the Best Paper Award from the Informed Transportation Science and Logistics Society. Let me see what's, so here, let me change the remove pin, remove, right. Okay, sorry. So Alex received the Best Paper Award from the Informed Transportation Science and Logistics Society, George Dantzig Dissertation Award from Informs, and the L.E. Rivet Medal from the French Academy of Science. He was named one of the leading academic data leaders from the Chief Data Officer magazine 2021 and 2022. Alex, the forum is yours, please.
Well, thank you so much for the introduction, Jinhua. Assuming that everyone can see my slides, interrupt me otherwise. Thanks everyone for joining. It's a real pleasure for me to get to present this work to all of you and also to get this feedback. I really hope you can feel free to interrupt me if anything is not clear, and I also hope we can engage in a discussion after this. So indeed, the topic of this talk is routing optimization with coordination between vehicles and customers. So this is joint work with Kai Wang, Shai Wang from and Wei Zhang from the university from Tsinghua University and from the Hong Kong Polytechnic University. And indeed, the motivation of this work is really about this, this emerging concept in ride-sharing and in transportation in general, where the customers and the vehicles can evolve in a coordinated fashion in order to basically make the system more efficient as a whole and hopefully create win-win opportunities. And I'm going to try to get to explain how we can power these new systems with dedicated optimization methods and with analytics algorithms, as well as look at their potential impact in practice for transportation operations. So at a high level, for those of you who don't know me, my research focuses on these emerging questions in transportation and logistics, with a particular focus on powering innovations, both vehicle innovation and digital platform innovation, with dedicated analytics and optimization capabilities. So what I'm going to present today lies under on-demand mobility. I'm also in parallel exploring a lot of questions around logistics decarbonization and how we can use collaborative decision-making platforms in order to consolidate operations, reduce empty miles, and ultimately make a dent toward decarbonization of the sector. I see some familiar names in the list of participants who are also very active in this area, so I'm happy to discuss related ideas as well. So this talk is really motivated by this by the type of products or in services in ride sharing that are usually referred by walking products that essentially provide some flexibility regarding where to pick up and drop off customers. So this is exactly the poll that Jinhua provided at the beginning of this call. So instead of serving customers from origin to destination, the platform has some flexibility to arrange for a mutually convenient pickup location and potentially a mutually convenient drop-off location between vehicles and customers. So when we think about it from an optimization standpoint, an operational standpoint, that sounds like, you know, a no-brainer, right? If people are willing to walk a little bit, and if the platform is able to find a better pickup and drop-off location, then what can go wrong, right? And the system should be more efficient, should be more optimal to some extent than it was before. But then it also raises a question, which is not necessarily if it's a good idea, but how to do it and how to power this new system with new algorithms. And here I would like to frame this question in two areas. The first area is, well, given what we used to do, given the routing that we have, given the way we used to operate the system before, now we need to have one more decision downstream, which is where to pick up passengers and where to drop off passengers. So that question alone enables smoother operations. So this is a very stylized view where you move from the red curve that basically will pick up everyone from door to door to, let's say, the blue and the green curve that enables smoother path, because now customers are able to walk and to therefore make the operations easier for the vehicles. Okay, so that's going to be the first part of my talk. But I'm going to argue that this is, so to speak, the easy part. The hard part is, now that you have downstream flexibility, how to re-optimize upstream operations. In that case, that means how to re-optimize the routing decision-making, the routing optimization, or the dial-a-ride problem in this in technical terms. That is how to power the ride-sharing system with downstream flexibility regarding where to pick up and when to drop off location, the passengers. So the decisions that we're going to optimize are which customers to visit, to serve, in which sequence, and with which vehicles. These are the upstream vehicle routing decisions. And in which locations and at what time. These are the downstream operational decisions. So the end goal is to solve this model called dial-a-ride with vehicle customer coordination. It's formulated on the right-hand side. I'm not going to go through all of this, but there is basically an integer optimization formulation that is either a linear, if we are considering a discrete network, or an L1 norm like Manhattan space, or a second-order conic optimization with mixed integer variables if we're evolving in the Euclidean space. The point is that this can be solved. I can give that to an optimization solver and, you know, end of story. The problem is that if I have an optimization algorithm that can solve a vehicle routing problem or a dial-a-ride problem, This is already a very hard and complicated optimization problem. Ride-sharing operate at a very large scale. These models are difficult, and so there is only so much we can do. Adding complexity by means of vehicle-customer coordination make the problem even harder. And on the left-hand side, I'm highlighting here a few of the additional constraints that involve, again, for those of you who are interested, additional big M constraints, linking constraints between different variables that make the polyhedral structure even weaker. And so basically, if I was able before to solve a dial-ride problem with 200 customers, I add more complexity. I'm no longer able to solve the problems at the scale that I need in order to actually power my ride-sharing system or my transportation system. And so basically what we're doing in this paper is that we're developing models and algorithms to optimize these operations in large-scale networks. So we're decomposing into 4 steps. Step number 1, single-stop optimization. Sounds trivial, but you have one vehicle that goes from an origin to a destination. You have one stop in between. The customer can walk where to stop. Okay. It's simple, but that's going to give us like the core engine that we're then going to use to solve more complex problems. And then the first more complex problems that we're going to solve is multi-stop optimization. You have a vehicle that goes from an origin to a destination. You have a sequence of customers that is given and where to stop to now optimize every single pickup and drop-off locations in that sequence. And now that we have that optimization engine, we can go into vehicle routing and dial-ride problem at a higher level. And now we are going to have a new modeling and algorithmic framework that will be based on subpath-based variables in time-space networks. And finally, I'm going to apply that in online routing optimization for ride-sharing systems. And on that practical front, I'm going to show some results that show some win-win-win outcomes, meaning that once we have that algorithmic capabilities, that optimization capabilities, then vehicle customer coordination can actually improve the efficiency of ride-sharing operations for the operator, lower costs, for the passengers, better better level of service, lower wait times, and potentially lower fares, as well as for the systems as a whole, with a potential impact on vehicles miles traveled and the footprint of urban transportation. All right, so briefly, I'm going to talk about the single stop optimization problem. So this is actually as I said, the very simple core sub-problem. You have a vehicle that goes from an origin to a destination that needs to meet a customer. The customer starts at the home location, but then the customer can walk. And then that's where the customer and the vehicle will meet, will stop en route for the vehicle from the origin to the destination. So I can formulate this as a very simple optimization problem, 3-dimensional, right? One is where, so 2D, and the other one is when, so 3 decisions, basically. This is a linear optimization problem with the L1 norm, a second-order conic optimization with the L2 norm. I can solve that, but I want to solve that very efficiently. And so what we are doing is that we're looking at the geometric structure, right? So like really going into basic geometry in that case. And we have a few lemmas. The first one is to say that the vehicle will never wait for the customer at the stopping location because the vehicle is faster than the customer. Then we're differentiating a few cases. Either the customer is able to walk in order to enable a straight path for the vehicle from origin to destination, or the vehicle will do a detour. So by kind of characterizing these simple cases, we're able to simplify the structure of the problem. And the most important result here is that we are reducing the search space by eliminating a lot of suboptimal solution. And what we can do is that we can solve the problem extremely efficiently. We are reducing the problem from 3 dimensions to 1 dimension in the Euclidean space. And in the Manhattan space, we are reducing the problem from a 3-dimensional optimization problem into a simple system of linear equations. So at this point, we have the core engine, which is single stop optimization. But now the first more interesting question in my mind that we want to solve is how to do that for multiple stops. So again, you have here a vehicle that goes from origin to destination, has a bunch of customers to serve on the way, and then we need to optimize where to stop for customer 1, customer 2, customer 3, customer 4, all the way to the destination. So now again, I could formulate this as a linear optimization or second order chronic optimization, but instead we want to decompose the problem. And the theorem that we have is that under some conditions, meaning that either the norm being differentiable, like in the Euclidean space, or if we have the Manhattan space, then the multi-stop problem can be solved optimally by solving single stop problems in sequence. So the way we're writing the problem here is that we are writing it either as a continuous space dynamic programming model. So in this case, once I am at a customer k-1, I'm going to optimize the location of customer k in order to minimize my travel time to the next location plus my cost to go function. If we view that as a dynamic optimization problem, is actually not straightforward. There exists no simple algorithm to solve that to optimality because we have continuous space. Right? We don't have discretized state variables or discretized decision variables. We could also view that as a convex optimization problem. And so we can reinterpret the algorithm that I'm going to present as a coordinate descent algorithm that has feasibility and optimality guarantees, even though we have a convex optimization problem with constraints, which is usually a difficult class of problems. So by exploiting the problem structure, we're able to solve the problem to optimality by solving, again, very simple problems iteratively. So I'm just going to give a flavor of the algorithm here. What we are doing is that, so imagine that this is the origin of the vehicle on the left, the destination on the right. In this case, I have 4 customers, and these are kind of their home locations, and they can walk a little bit. So I just want to illustrate very simply what we're doing. The first step is that, so we are starting backward. So we're proceeding backwards. So we're starting on the right. And then what I'm doing is that I'm going to fix that location, and re-optimize the location in between. So now the tail is optimal, and I'm going to move one step back. So now I'm going to fix that location, and re-optimize the one in between. But since I re-optimize customer 3 in that case, customer 4 may not be optimal, so I'm going to re-optimize the tail. Okay, so now I have an optimal sequence for customers 2, 3, 4, 5. And now I'm going to, again, move one step backward to customer 3, and then move one step backward to customer 2, move one step backward to customer 1. But now that I have re-optimized customer 1, my tail is no longer optimal, so I need to re-optimize downstream. And once I do that, I converge to an optimal solution. So in other words, we are proceeding in 2 loops from a dynamic programming standpoint. We have a backward induction process, but then at every step of the backward induction process, we're re-optimizing the inner loop in order to always ensure optimality of the tail. And that is enabling us to have a decomposition structure that, again, solves multi-stop optimization problem as a sequence of single stop optimization problem. And per the previous section, I can solve single stop optimization problems extremely efficiently, which now goes some way into saying that we can solve the multi-stop optimization problem very efficiently. Okay, so at this point, I just wanted to show a little bit of like what's going on under the hood. But we have only solved the first part of the problem. So if I go back to this slide that I presented before, I have essentially solved the downstream problem, which is that I have a sequence of customers to serve. I have a sequence of pickups and drop-offs. And now I need to optimize where and when to stop. Good. But now the question is how to go backward, how to go upstream, how to re-optimize routing operations, right? And so this is, excuse me, taking us to the world of vehicle routing optimization. So we're defining 3 problems in this paper. Number 1 is the vehicle routing problem with vehicle customer coordination. The second one is the diagonal ride problem with vehicle customer coordination. So the diagonal ride problem is probably the most relevant one to ride sharing, because in this problem, every customer has an origin and a destination, whereas in vehicle routing, they just have one location. And finally, we're implementing the problem online with batching and optimization in order to demonstrate the applicability of the methodology that we're presenting in this paper in real-world ride-sharing systems. So we're using taxi data from New York City. We're batching every 10 seconds and optimizing the dispatch of vehicles. And then we're kind of carrying information from period to period, and every 10 seconds, we're re-optimizing. So what I really want to be able to do is to solve the problem with hundreds of customers in seconds, so we can actually really really power these operations in practice. So in order to get there, we are first going to look at the dial-a-ride problem with vehicle customer coordination in such a way that can solve large-scale instances in seconds or minutes. So we can solve realistic problems instances in seconds. So here I want to take an aside. This is probably the most important slide from this section, and this is like a modeling slide. For those of you who are working on vehicle routing or dial-a-ride problems, there are, I think, two canonical formulation techniques that are used. On the right-hand side in that slide, you have arc-based formulations, where you're optimizing decisions along the lines of, do you pick Alice and Bob in that order, or do you pick Alice and Charlie in that order, and then Charlie and Bob? So you're like basically optimizing at the level of connections. On the left-hand side, you have much more disaggregated variables where you are optimizing over an entire route. So what is a route? It's for one vehicle. You start at home, you go and pick up Alice, you go and pick up Bob, you go and pick up Charlie, you go and pick up David, and so on and so forth. You go and drop off, you go and drop off, you go and pick up. So you're optimizing over entire sequences of decisions. Technical terms, that leads to set partitioning formulations that are typically solved with column generation and branch and price algorithms. And what we are doing in this research is something that is in between. The problem with arc-based formulations is that they are very weak. That's basically the first formulation I gave, very weak polyhedral structure and not scalable at all. The problem with route-based optimization, I mean, on the positive side, they are much tighter, but on the negative side, there is a huge number of routes, exponential number of routes that make them usually intractable as well. And what we are proposing in this case is an intermediate formulation where we're optimizing over subpath. What is a subpath? It's basically a route, but it doesn't start at the beginning of the day. It doesn't end at the end of the day. It starts whenever a vehicle is empty, and it ends whenever a vehicle is empty. So a subpath could be pick up Alice, pick up Bob, drop off Alice. I was empty at the beginning, I'm empty at the end. Another subpath can be pick up Alice, pick up Bob, drop off, pick up Charlie, drop off Alice, empty at the beginning, empty at the end. The benefit of this is twofold. Number one, we have fewer variables, but still we have a very tight formulation for the optimization. So that's a dial-a-ride argument. But then on top of that, within each subpath, I can use exactly my multi-stop optimization from the previous section in order to optimize where and when to stop. So that's the vehicle customer coordination argument, right? So we are kind of killing two birds with one stone with this formulation. We are improving on the dial-a-ride formulation, and we are enabling the integration of the vehicle customer coordination mechanism. So, and then what we do is that we put this subpath into this time-space network. So in that case, and then we're combining subpath in order to go all the way from the origin to the destination. So the overall algorithm has three components. One, we are creating, for every subpath, I can optimize where and when to stop. Number two, I'm generating a bunch of subpaths via dynamic programming. And number three, I am combining the subpaths together via a time-space network optimization that is formulated in this box. And as you can see, it's a much simpler and therefore much tighter formulation, relying on very typical flow balance constraints. Right, so on the top here, you can see another representation of these dynamics. So we have, in this case, 4 subpaths or trips, where I have pick up, drop off. So 2 passengers share a ride. Then we have one pickup, one drop off. The passenger is by himself or herself. Then we have a longer subpath with 4 passengers total, and then the vehicle goes back to its destination. All right, so now let me turn to some results. So I said at the beginning that my goal was to solve large-scale problem instances. So for the small instances, we are much faster than off-the-shelf solvers. Again, I could solve the problem with as a mixed integer linear or second-order cone optimization. The problem is that with as few as 5 customers, that would take 60 seconds, so 1 minute. So not really adequate for real-time ride-sharing operations. So 60 minutes with off-the-shelf methods, with our algorithm, we solve it in 1 second. Okay, that's promising. Medium instances, that's where the solvers can no longer solve it. It takes 1 hour with, as few as 7 or 8 customers, and we can still solve 25 customers in 1 second. And then the large-scale instances, we actually get optimal solutions when the solver doesn't even give us a feasible solution. And so much better scalability is a technical answer here. And then I wanted to circle back to this idea of downstream and upstream optimization. So how do I establish this? The first one is, let's take a 2-step decomposition approach, where in the first step, I'm optimizing diagonal ride operations as I was before vehicle customer coordination. We're not the first one to think about routing optimization. Of course, we have good algorithm for that, but then you fix the sequence and you re-optimize where and when to stop, right? In other words, simply saying, Uber had algorithms in 2015 or 16. Then you fix the sequence using these algorithms. Then you say, okay, what if I could actually ask people to walk? Let me find marginal deviations from the pickup and drop-off locations in order to make the operations more efficient. I'm going to do better. The answer is yes by 0.5%. That's the blue column. Why? Because once the sequence is fixed, there is so much you can do. There is not that much deviation, that much flexibility anymore. If, however, you embed that flexibility into routing optimization to re-optimize the sequence of stops and the sequence of customers, then your profit can increase by 20 to 30%. That's the red box over there. Okay? And so that's really showing that the impact of the benefit of this technology is not just the business innovation and the platform and the flexibility, but also the dedicated optimization model to re-optimize how we operate now that we have more flexibility. And finally, how does that play out in ride sharing? So here we're using, again, real world data from the New York taxi system. We have this map on the right that shows basically where all of the passengers are requesting rides over a four-hour period during a busy morning. But here the scale of operations is obviously much higher, right? We're talking about tens of thousands of requests per hour. They're arriving dynamically. So, we have to adjust the algorithm in order to capture this scale and online arrival. So the way we're doing it is batching and optimization, re-optimization every 10 seconds. So once you do that, then you go back to like instances where you have 20, 30, 40 customers every 10 seconds. And so so that is actually something that you can solve in seconds. So I just want to, I'm going to skip through the technical results, and I want to spend the last 5 minutes on the practical results. So what do we have here? So the first result that I want to show is that the vehicle customer coordination for pickup and drop-offs increases profit for the ride-sharing operator by 6%. So that's, first of all, the benefits of vehicle customer coordination, walking products, again, when powered by dedicated optimization algorithms, such as the one developed in this paper. This is not marginal, right? 6% can translate into millions of dollars annually in a system of the size of Manhattan, right? So obviously there is significant improvement opportunities in this context. Okay, the second result in blue is that most of these benefits actually come from upstream re-optimization. So what do I mean by that? I'm decomposing the profit increase into mere cost savings at the downstream level, given, I used to serve customers, now I serve them at a lower cost. That is contributing 14% of the 6% increase. The remaining 85% is due to re-optimizing who to serve and in which sequence, right? So again, the idea is that once you have an innovation downstream, it's not only the innovation and the flexibility that is providing benefits, but we need to really think about how that is incorporated into the optimization algorithms to power, in this case, routing and dial-a-ride dynamics. Number 3 is that we find that the flexibility for pickup locations is much more impactful than the flexibility for drop-off locations. And that was actually, at the beginning, we were a bit surprised by that, but it makes a lot of sense, actually, because when you have a pickup, then if you can walk a little bit before you get into the car, then it's mutually beneficial. You get a pickup earlier, the vehicle doesn't go around the block to come and pick you up at your house, but then you can walk for 1 minute or 2 minutes. And then it's better for the vehicle because it doesn't have to do the detour, but it's also better for you because you are getting to your destination faster. For drop-offs, it's really good for the vehicle because the vehicle can be lazy and say, hey, I'm just going to drop you off here, but then you do the rest, but it's actually negative for you. So it's less synergistic between the vehicle and the customer. So from a practical standpoint, transportation operators should perhaps invest more in terms of flexibility for pickups than for drop-offs. Another insight here is that we find synergies between vehicle customer coordination and ride sharing or ride pooling, meaning that once you have that flexibility, you have actually more shared trips, more consolidation, and vice versa. When you have ride pooling, you can actually increase the incidence of vehicle customer coordination to a more significant extent. And then what we do is that, okay, so how does that work for the system as a whole? So the one thing that we find, the first thing that we do is that how do we make it work? So we're not really optimizing pricing, but we're saying, can we design a discount scheme in order to share the benefits between the operator and the customer? And we actually find that the discount can be quite significant, around 16% of the rides on average for the customers. And finally, we find a significant reduction in the vehicle miles traveled through that mechanism in this case, by 15 to 30%. And an even more significant, so basically we are serving more customers with fewer overall miles. So which means that the reduction in vehicle miles traveled per customer is even higher. And so what that tells us is that we end up with win-win-win outcomes where we increase the profitability of the operator by 3%. 3% is simply 6 divided by 2 because we have profit sharing between the operator and the customer. More customers receive a service, 6% extra coverage in terms of demand. And we are mitigating the environmental footprint of the urban mobility system because we are consolidating operations, leveraging flexibility to avoid unnecessary miles, and ultimately cutting vehicle miles by 15%. All right, so this is my talk. This is the summary slide that I had at the beginning. So single stop optimization, multi-stop optimization, dial-a-ride, and online routing optimization for ride sharing with ultimately win-win-win outcomes by introducing flexibility downstream and re-optimizing operations upstream with dedicated models. Let me maybe stop here and I'd love to answer questions.
Great, yeah, thank you so much, Alex. Yeah, I noticed that in the audience there's several OR and transportation expert, so I'll invite some of the to give some comments or questions, right? First of all, let me know there's Professor Tom McNanty, Professor Song Gao, Professor Robert Freed, Professor Florian Dando. Just a few I just noticed. I must have missed many. So for now, let me invite Professor Robert Freed to give some remarks or questions. Robert, please. You're on mute.
Thank you. Sorry. So, wow, Alex, really interesting talk. What can I say? I have to say, as an optimizer, of course, I couldn't help but be fascinated by the stuff related to, both implications and what kind of algorithms were used and the creativity there, et cetera. But I also noticed, and perhaps in a way that you could not, the number of questions and comments that people were putting in the chat so quickly, in so many different ways, in so many different arenas, having to do with, what about penalties for cancellations, the issue of flexible pickups. I was in Manhattan just a couple of weeks ago, and I think I would imagine flexible pickups are much more valuable there because of the one-way street configurations. Okay, that's just huge. And I love to see the carbon implications at the end. And I think that's all I'm going to say at this point, because I think the number of people who are dying to interact with you on this in real time now is quite large. So great talk, Alex. Thank you.
Thank you so much, Rob. Your point on Manhattan is very important. And actually, there's a lot of data engineering that went into the last case study that I presented, because here we're not evolving in the Manhattan distance, despite the name. We're not evolving into the Euclidean space and continuous space, but we have a very discrete network. And actually, we used OpenStreetMap data in order to calibrate travel, all the things, one-way street, travel times, and all of these things to actually capture these things. So there is a lot of things that are going under the hood to make these as realistic as possible. And that's also one of the reasons why a little bit of flexibility can provide a lot of benefits. As I said at the beginning, on average, the walking distance is 100 meters. So think about it as like 2 blocks, not a lot, but that is really going a long way in terms of avoiding these types of detours because of one-way street and this type of thing. So so that's a great comment.
Great, yeah. Thank you, Robert. So Alex, I will start with a couple questions, and then John will give you a bunch of, there's so many audience questions there, right? So start with is the asymmetry between pickup and drop-off, right? So you mentioned that they are asymmetrical in the benefit point of view, but also in the coordination cost point of view. We also noted that pickup requires much higher cost or effort of coordination than drop-off. Drop-off is kind of trivial, right? But pickup involves the navigation, the two have to find each other, find a reasonable, safe place to parking. And also from the consumer point of view, waiting at home versus waiting at some street corner, that mean very different things, right? The sense of safety, the sense that I can do something useful. Yeah. Also relate to the fact that for Americans, if you were a public transit user, walking a little bit, wait is norm. But for many of Americans who never have the notion of public transit, they've ever been driving door to door, that's kind of a major cultural shift on this, right? So what's your remarks about this, the asymmetry and also the behavior aside?
Yeah, that's a really good line of questions. So talking a little bit about the asymmetry, I think that you're entirely right. That's a good read of the results. And that's also a good read of the practical implementation challenges. Basically, the motivation for this work and a lot of my research in general is that digitization is enabling more coordination. And therefore, we have the ability to use all of the real-time sensing data in order to actually power that coordination. And then the question that I'm asking is how to do that. And it's actually not that trivial to actually really understand how, where to coordinate and how to coordinate. And here it's really we are surfing up the wave of digitization and developing the right optimization methods for this, and showing when it's most beneficial. I think that your point on behaviors is extremely important, and there are a couple of points that I would like to make here. Transit users or not, or aside, it comes at an inconvenience to walk there, and to especially when we start looking at November weather and being cold outside and all of these things. So I think that there are two ways in which these results can be used. Number one is that right now there are some, the platforms have a very good understanding of who is more price sensitive versus who is more service quality sensitive in their user base. Actually, the users can select a service or not. And so if you can actually just use customer buy-in as a proxy for like who's the population under interest, and then you can use the algorithm to actually power that. And then number two, I also think that the model that we have can be used to answer other questions, which is when is it really valuable? And maybe you have a couple of pickups for which walking 100 meters can actually mean so much in terms of system-wide efficiency, and some others where, sure, my model does recommend a little bit of walk, but honestly, there is an almost optimal solution where the customer doesn't walk. And so maybe another use of the model would be to say, well, what if you actually reduce the number of walk by a factor of 2? Which one would you prioritize? Because again, behaviors aside, it's an inconvenience, and you want to minimize that inconvenience. So point well taken. And I think that this is really where not only the development of the model, but the use of the model can have impact by itself.
Great. Second question, you mentioned that the win-win-win solution here, right? So in the end, the optimization can achieve, say, an overall benefit to society. But how do you allocate the benefit between the different parties, right? The consumer, the operator, and the system as a whole. So is this a business strategy decision? Is this a value judgment decision, or this is very much a neutral and purely a scientific decision?
It's all of the above, probably. But in this case, what we wanted to do is like just to identify win-win-win opportunities. And actually, there exists a menu of win-win-win opportunities, meaning that there are multiple ways in which we can think about that profit sharing. That, in other words, it's not that there is one little super sensitive point where we have win-win-win. There is like a robust interval where we do have win-win-win. The customers get served more with faster service. I saw a comment about time windows in the chat. This is extremely important. We have very tight time windows. We are talking about ride sharing and therefore time sensitive customers. So you're more likely to get a ride quickly with flexibility. The operator is serving more customers at lower cost, and we are reducing the environmental footprint. And that is valid over a relatively wide range of parameters. So there are multiple profit sharing opportunities. Now, to answer your question, I think that it really goes back to the previous question, because now it comes at an inconvenience. Therefore, you need to incentivize people. And the right incentive mechanism may differ by person to person. So you can actually even think about personalized rebates, personalized discounts, personalized incentives in order to incentivize this behavior, because again, it's win-win. And so that's how we think about it. But at this point, this is really where my model ends. And that's, I think, a very good question for future research.
Very nice. Thank you. Yeah, I also noticed that several people from the industry coming at like Furman from Lyft and many others. Here, I just ask you the question of how much the industry is willing to embrace this type of thinking and experiment, right? We know that Uber did try this before, then tried it, they stopped. They said, where's the industry state of practice here?
Yeah, I think that this is it, right? It was, I mean, I started this research when it was actually starting, and was like, wow, that sounds very exciting. How better can it be, right? And then you get into all of the problem that you mentioned, and the behaviors and the inconvenience. I don't believe that this is actively used anymore, and I'd love to hear also from the crowd to get examples, counter examples potentially. But I do have examples of systems that actually do leverage that type of flexibility. An example is like when we start thinking about microtransit, for example. Then here we do have, on-demand vans that will provide transportation services to a group of people, and then you have a lot of embodiments of these systems that do not necessarily do door-to-door, but can actually consolidate demand in what is usually known as virtual bus stops. And now the question is like, at which virtual bus stops do you want to stop? And why, and how do you adjust these decisions dynamically based on like who is in your van and who's requesting the service later on. So so I think that the methodology that we developed in this research is not only confined to Uber Express Pool and Lyft Shared Saver, but has a lot of applicability across the transportation ecosystem. Whenever we have that type of digital fueled flexibility regarding where to stop. You mentioned at the beginning that we're doing parallel work in microtransit, and this is really building upon that line of work in order to like design demand responsive transit systems as well.
Indeed. Thank you, Alex. John, pass you for the audience question.
Alex, as always, we had a really active chat, and we will share this with you because there's a lot of interesting questions and comments. I'm going to start with Michael Long, who's a graduate student here at the Department of Urban Studies and Planning. And he asked a question that actually I had as well, which is, let me just read what he wrote. He said, what if we had a transportation system where rides are only requested between predetermined stops, let's say every 100 meters, and customers self-choose between these discrete points instead of in a continuous space? Question, would that make it easier to optimize and also make it easier to operate and regulate these vehicles? So basically cities could kind of make these places. They could provide shelter, etc. You walk to a place where if it's pouring rain outside, it's actually a more pleasant experience, although I know you said you don't want to actually wait at those places. So do you have a feel for this, how city design could actually ultimately interface with this type of vehicle to customer system that you described?
So that's an excellent question. Thanks, Michael. I have three levels of answers. The first answer, the short one, is yes, great idea, let's do it. And the second level is that I have some results that I didn't show today. So let me first tell you how we implemented the Manhattan problem. The Manhattan problem, again, doesn't evolve in continuous space, right? So we have a couple of we have a few candidate stopping locations. What we consider at this point is like simply intersections and hotels, right? So whenever you have a hotel, you can actually, you have a little curb and you can stop here. And otherwise, we're just saying we stop at the intersections and you are assigned to an intersection. So we could replace this network by what you're suggesting. And actually what we find is that the density of the candidate stops does not have a huge impact on the efficiency of operations, meaning that if the city doesn't want to have that at every intersection in Manhattan, but maybe every other intersection, I don't think that you would leave a lot of money on the table. So that's a positive result, right? The positive result is that you could design a few well-chosen virtual bus stops that would be more, just nicer to wait at, and that could actually make the system, I think, more appropriate to this type of services. However, the other answer is that the one thing where I think you would be leaving money on the table is if you left the customers choose where they want to, which virtual bus stop they want to be picked up at. Imagine that. So just to take a simple example, in Manhattan, you're on 5th Avenue on 45th Street. You would decide whether you're going to 43rd or 47th. But in my system, in this algorithm, the system design chooses that for you, which one you go to. And this is actually important because once the system has that flexibility, it can optimize your ride in view not only of you, but actually the other systems, the other users as well, and create more efficient routes for the drivers. And so I have a hybrid answer saying that I think that city design can play a huge role toward that transition, but there needs to be some sort of centralized control by the platform in order to really maximize the efficiency.
Excellent. Another question coming from Gordon Bauer, and it was when you were talking about the 6% profitability that you saw. And so the question was basically about the relationship with the density. So obviously, Manhattan is maximum density. I was in a lift in Los Angeles yesterday. How would that 6% profitability play out in different cities around the world based on density?
Short answer is I don't know. It's I mean we would need to apply the model elsewhere and to do a systematic experimental design. But I can try to think about it out loud today. The main I think that the benefits would be there and would be robust, and we do observe the same thing in different in also randomized experiments that we have done. The one thing, however, is that the benefits do increase when you have opportunities for carpooling or ride pooling. And that's also why this system is so important in microtransit, because ride pooling is really maximized, right? When you think about higher capacity vans as opposed to single occupancy vehicles. If you have such a low density that all of the rides are by themselves, you're still going to have some benefits, but they are going to be smaller than 6%. That's my guess. So you probably do have, I would say that the two main parameters are density and kind of type of service. If you have an axis that is single occupancy vehicles, ride pooling, and microtransit, I think that you would really increase your relative benefits associated with vehicle customer coordination once you move from left to right on that axis as well.
Excellent. Okay, and as Jinhua mentioned, I mean, we do have some people from industry on the call as well. So I'm thinking of Mike Furman and Sar Golde. If so, I'm just positioning you guys. If you want to jump in with a comment or two, please do. In the meantime, I'll pose another question, which was put forth by Allison Miskell, which is, you know, one of the issues we're seeing with corner-to-corner type services is that drivers, riders, agencies do not feel safe at some of these various organically derived pickup points. My question is, how can we algorithmically operationalize this with safety as a key factor? It's a tough question. Do you have any thoughts on that?
Yeah, this is a hard one. I think that my main answer here would go back to your earlier question about formalizing the virtual bus stops through city design. That can be one area. There is another line of research that is also important in that regard as well. I'm happy to share the paper for those of you who are interested. It's done by Julia Yan and Sebastian Martin, who are two MIT grads now at Vancouver, UBC, and Kellogg Northwestern, who are basically taking the system that we're proposing in this research, but instead of really optimizing dynamically, they're optimizing more statically, meaning that every time you're going from the same origin to the same destination, you're going to be assigned to the same stop. And basically, it's kind of an 80-20 argument, right? You're providing 20% of the flexibility and you're getting 80% of the benefits. I think that this can go actually a long way in terms of safety, because safety comes with familiarity, right? If you start going all the way to the same place and you start being comfortable with that place, then it can actually increase the acceptability. That also goes back to the behavior question from Jinhua earlier. So these are some pointers. I don't have a magical answer here, but I think that city design can play a role, and also platform design can play a role.
Excellent. There were a couple questions just about the kind of environmental implications. So please feel free to comment generally on that, maybe perhaps the relationship with CO2 emissions, greenhouse gas, et cetera. Saidi had a question, which is, from a demand modeling point of view, would such a flexible ride-sharing service attract more passengers from conventional public transit? And if yes, what would be the environmental footprint implications considering the entire transportation system? So, I mean, we've seen these types of studies that have shown that, you know, ride hailing has drawn people away from public transit. Just any thoughts you want to offer on this topic?
I mean, I have two answers here, right? Is that one is that it depends on like what it's displacing from, and if it's displacing from self-driving, for example, there can be even further benefits. If it's displacing from public transit, indeed, that can be eroded. The other thing is that this is a point that is very well taken, and that's actually one of the main drivers or the main motivations underlying the other study that we're doing, where we're optimizing that type of system for microtransit. And I think that if then we can leverage similar technology for high capacity vans or for buses and these type of things, then we really have the opportunity to not only make ride sharing more efficient, but also public transit more demand responsive and more efficient, and therefore maybe actually drive more customers and passengers to public transit systems as well. I'm also coming back from Manhattan this week because we had a meeting with Via Transportation where we're actually trying to deploy these systems in shared vans and shared bus systems. So it's a complex answer. It's a complex question. Well taken. I think that the goal of these algorithms is also to kind of enable all of the systems to operate more efficiently. And I think that there exists a sweet spot somewhere where you can actually provide a higher level of service for passengers, to enable more providers to coexist profitably in that ecosystem, and at the same time mitigate the overall footprint.
Great. Okay, and maybe just one super quick question on methodology. Question from Atkin Obafemi, which is what programming language or simulation tool was used to produce the results?
A lot. So a lot of pre-processing of data in Python from the OpenStreetMap data, from the Manhattan taxi data, from the GIS data in general. And then for the optimization, we use a combination of Julia and C# because we were split between MIT and Hong Kong Polytechnic University. We use different languages, but we could communicate with these programming languages. So yeah.
Fabulous.
Great. Thank you, John. Thank you, Alex. So here, as we mentioned at the beginning, that Professor Jacquillat actually prepared a two-part presentation for today. And given the time, I suggest we only focus on the ride-sharing part. The same style of thinking can very much apply to microtransit. So how do you take advantage of flexibility and coordination in the microtransit context? For that, we invite Alex back again for the future session. That also, one more thing, Professor Charles Asinimi in the audience asked, how do I get my graduate student to be part of the future webinar? For that, two answers. One, this webinar is open to the public. Please feel free to forward the invitation to the student, invite them. But more deeply, at MIT, this forum also works as an elective class. It's a short 3-credit class, right? Where we're happy to share the syllabus with all the educators in the audience. I use this as a class in your university. We're very much happy to support that as well. So with that, please everybody join me. Thank Professor Alex Jacquillat for this.